Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss the Virial equation. Let's begin. If we write the equation of state of gas that represents the functional relationship among the properties like pressure, molar volume and temperature T, and which can be expressed as the function of pressure, volume and temperature is equal to 0. That represents the equation of gas. That the functional relationship between pressure, volume and temperature. From this expression, if any of the two parameter of a gas, means if pressure and volume or volume or temperature or pressure or temperature, any two of the parameters of gas are known, then the third parameter can be calculated by using that particular equation of state. In experiments, if we plot the graph between the product of pressure volume in y axis and in pressure in x axis, PV as a function of pressure at constant temperature, then a graph is plotted. If we take the temperature, as we have already studied, these are the temperatures as T1, T2, T3 and T4, and the temperature orders are T4 is less than T3 is less than T2 is less than T1, that I have already discussed. Means all gases exhibit a remarkable property in thermodynamics, that as pressure approaches to 0, the product PV approaches the same value for all gases at the same temperature. That graph indicates. This fundamental property of gas explains that the limiting value of PV as P tend to 0, that limiting value of PV at P tend to 0 is independent of the nature of the gas and depends only on temperature. That is independent of the nature of gas. But depend on temperature only. As P tends to 0, P approaches to 0, then the product of PV as P tends to 0, that is independent of the nature of the gas and depend only on temperature. Then what happened here? The relation between PV and P can be expressed for a real gas by means of power series, which is known as the Virial expansion of this gas. So, the Virial expansion, since we know at P approaches to 0, that is independent of nature of a gas but depend only on temperature, then we write the virial equation as the relation between pressure volume PV and pressure, the product of pressure and volume and pressure can be expressed for a real gas by means of a power series known as virial expansion of the form of that virial expansion, the product PV, pressure into volume, is equal to A whole into 1 plus B into P plus C into P square, like that series proceeds, where A, B, C are known as virial coefficients, where A, B, C are virial coefficients, and these are named as A as the first virial coefficient, B is the second virial coefficient, like that, C with the third virial coefficient, and so on. That proceeds like this. In general, if we write in general, if the pressure is very large, then the number of terms in that of virial expansion will also be large. This is the virial expression, that is the virial expression, So, if pressure is very large, then the number of terms in that of virial expansion also be large. On the other hand, if the pressure decreases and approaches to 0, then the product PV approaches the same value for all gases at the same temperature. So, we use the term as, if in general we say, if the pressure is very large, then the number of terms in the virial expansion will also be large. On the other hand, if we reverse it, if pressure decreases, and it approaches to 0, what happened? Then the product PV, then the product PV, in the product PV approaches the same value, approaches the same value for all gases at same temperature. As we take that point from this type of graph at same temperature, that can be written like this: the limiting value of limit where pressure tend to 0 and the product of PV is equal to the first virial coefficient A. When PV taking the limiting value P tends to 0, so that virial expansion, limiting value of that virial expansion will be A. Look at here, here the virial coefficients are in decreasing in magnitude, means the value of A will be the greater than of value of B, greater than value of C, greater value of D, and so on. This is the decreasing order, the magnitude of virial coefficient. This is the decreasing order, decreasing order of virial coefficient magnitude. Virial coefficient magnitude. Hence, we can say that the first virial coefficient is a function of temperature. This is the first virial coefficient A, which is the function of temperature and temperature only, since it depends upon the temperature and does not depend on the nature of the gas. So, A, here we write first virial coefficient is depend on temperature only, not the nature of gas, not the nature of gas, as we confirm from that equation. But from the equation of state, we know that PV is equal to RT, or PV is equal to nRT, n with the n number of moles. So, PV taking the limit as P tends to 0, product of PV is equal to R into T. That value will be A, or limiting PV is equal to A. So, A is equal to RT, A is equal to RT here, where R is the molar gas constant. No things, R molar gas constant, universal gas constant. Mathematically, the value of R can be written as, here the value of R is equal to limit P tends to 0 PV divided by T. This is the limiting value of R. Thus, the virial equation of state can be expressed. Thus, the virial equation of state can be written as PV is equal to RT, limiting value of PV is equal to RT. So we write PV by RT, PV by RT is equal to 1 plus B P plus C P square plus dot dot dot. Look at that expression. Here PV is equal to A whole into that much. In place of A we substitute RT. So PV by RT is equal to that equation. Okay. Here that equation was introduced by the scientist Kamerlingh once. That equation is introduced by Kamerlingh once. That's why according to his name that equation is known as Kamerlingh once equation. Kamerlingh once equation of state according to the name of the scientist Kamerlingh once. Here the ratio of PV by RT, PV by RT the ratio PV by RT is known as the compressibility factor. Compressibility factor, and which is denoted by capital letter Z. The ratio of PV by RT in the left hand side of that of equation, which is known as the compressibility factor, which is denoted by the letter Z. For ideal gas it will be 1. For ideal gas Z is equal to 1. The compressibility factor is 1 for ideal gas. What is the physical significance of that of compressibility factor? The physical significance of that of compressibility factor that gives an indication of the extent of deviation. Physical significance of compressibility factor is that gives an indication of the extent of deviation of gas from the ideal gas behavior. How that real gas is deviated from the ideal gas behavior, that can be studied by using the compressibility factor. So that is an indication of the extent of deviation of gas from the ideal gas behavior. So with the help of this visual exercise we understand what is Virial equation. Remember a point here, the word virial, that is derived from the Latin language, which means virial meaning in Latin language, virial means force in Latin language. Virial equation, virial expansion, how that is related to the temperature, and finally we take the expression what is PV by RT, that is the compressibility factor, and what exactly the physical significance of that compressibility factor. So with this useful and informative notes, let me wind up this session. Thank you.